functions. So in this part, we will learn the basic concepts in parallel programming. Also, we will gain knowledge on the tools for parallel programming in different languages. Here, this day, we will learn about Julia, and also we will get familiar with the tools to monitor the usage of resources in our centers. So what is parallel programming? It's the science of writing code that execute tasks on different computed units called cores. Yes. And the crucial part is here that the tasks are executed simultaneously. Yeah. So previously, the computers had a single core per central processing unit CPU. Yeah. And because of that, a single computation could be done at a time. So, and this is called a serial program, that it is executed on a single core. Yeah. So nowadays the architectures are more complex than that, and we can have, for instance, some cores that share some available memory, as in this case. So in our case, for instance, at HPC2N, we have some machines that have more than 100 cores that share some memory, for instance. Yeah? So this is more complex. Um, this is called shared memory. There are also some other architectures that are called distributed memory. And in this case, yes, although there is some shared memory in some of the cores, right? So they can also exchange data, yes, uh, across other cores, yes. Uh, but notice here that the memory is not shared, yeah. So in this case, they get data from the other cores by sending and receiving messages. And this type of architecture is called distributed, right? So to differentiate it from the shared memory architecture. So this is a more realistic picture of a single node on Kebnekaise. So here we have 14 cores, yes, per socket. So in total on a single node, we have 2 times 14 equal to 28 cores. And here, these 14 cores share some memory, in this case, 64 gigabytes. So in total per node, we have twice this number, which is 128 gigabytes. So here, there is some important feature of the shared memory in that the available memory for the cores has a different bandwidth depending on the type of memory that you want to target. For instance, if you are working locally with the local memories here, L1 to L3, the bandwidth is very high, right? But if you want to move to the upper level, so the bandwidth is lower. And even more, if you want to transfer messages across the different cores that don't share some memory. So this is one advantage of using the shared memory architecture. So, so why is parallel programming needed? You have seen that currently the architectures of the nodes or the computers it can be very complex, right? So if you put your program simply on these machines, it doesn't mean that it will run on all the cores and exploit all the hardware features like a memory that are present on the cluster, but you need to make your code aware of that, and that's why a parallel programming is needed. So for instance, in a HPC cluster, as LUNARC or UPPMAX or HPC2N, we have this pattern here where we have many computing nodes. And here, if you zoom in, you will see a picture that I showed before, where some cores share a memory, and they also can exchange memory across them. So besides this, to make your code parallel, you also need a way to send the jobs from the login nodes to the computing nodes. And that's why we mentioned before the batch scripts in the previous section. So something that can happen when you move your workflow to the cluster is that you can underuse the cluster if you don't pay attention to the resources that you are allocating, or even in the other side, you can exceed the resources that you allocated. So it's important to keep an eye on this. So we have tools in our centers to monitor the allocated resources. And here there is a tool that we have at HPC2N called job usage. So if you click on this link, you will see a picture of the graphical interface that you have at HPC2N. And this gives you the statistics of your job when they start running, right? So you can see, for instance, the CPU utilization, the memory on the CPU side, and also the usage of the GPUs if you are using GPUs, and the memory usage on the GPUs. This is a nice tool that I frequently use for the jobs. So the UPMAX, you can use a top once you are in an interactive session to see how the resources are used. So there are different types of programming paradigms that you can apply to your code. And there are also some existing libraries in Julia that allow you to have some parallelization layer if you don't want to code them, yes, by yourself. So the first model is called threaded programming, and in particular for low level programming languages such as Fortran, C, C++, one can use OpenMP as an standard API to parallelize the code. Then you can tune off and on these libraries by setting some environment variables. And in the case of OpenMP, for instance, you can use this flag, just as an example. Notice that higher level languages, in the present case Julia, can make use of external libraries, especially for linear algebra. Here I am listing just a few of them. LAPACK, BLAS, there could be also FlexiBLAS, for instance, that are used under the hood to compute linear algebra operations, for instance, in NumPy. And then there could be some internal mechanism to tweak these libraries, as in this case of the OpenMP that I mentioned before. Yes, so you can tweak these libraries to use different types of threads. And notice that the languages can also have their internal threaded mechanism, which can be confusing. So here I wrote some warning. So you need to check if the libraries or packages that you are using have a threading mechanism. You can also use the tools that are available at your center to monitor how the resources are being used. Yes, for instance, in our case, and that's why I like to use this tool, because sometimes you request some number of cores, and then you immediately see that you exceeded the 100% of the CPU utilization, which means that most likely uh, some cores are overused, and this is a signal that maybe you are using a threaded mechanism inside a parallel program. So this is specific for Julia, and this is one case that could get to an over-exceeded resource. For instance, for some linear algebra operation, Julia supports some threads, yes, and this can be uh, set with some environmental variable, right? And imagine that you want to run this type of code for linear algebra, but within a parallelized loop in Julia. And you allocate just some number of processes, right? So notice here that the processes or the iterations will be parallelized over n processes, but in addition to this, you are setting some extra threads for each iteration. So in that case, you will most likely exceed the number of resources unless this number of thread is explicitly set to 1. And this is when you will observe in your usage that you are over exceeding the allocated resources. So here is something more specific for Julia. Julia has a mechanism for setting the threads. And this is done with the threads flag in Julia. And X is the number of threads that are used. And this is important. Julia calls the threads Julia threads, which are not to be confused with the linear algebra threads that can be set with the OMP threads variable or even BLAS num threads, for instance. So besides the shared programming, we have also the distributed programming. And here, the point is that this allows you to scale the code over more than one node. Yeah? If you remember, in one node, you can have some shared memory, but once you go to more nodes, you cannot share the memory with the core, so you need to exchange the information between them. And then one API that is frequently or commonly used for that is MPI, is Message Passing Interface. And here, this is not straightforward to use. You need to learn this MPI protocol just to make use of the distributed computing. So more specifically for Julia, you can set some number of processes, right? And they can start with the dash P, yes, and X, where X is the number of processes that you can use. And in the case of MPI, you will need to install the MPI package. So if you have some large arrays, Julia provides you with some tools, and one of them is Dagger, which is heavily inspired on Dask according to the developers. And it supports distributed arrays. Yes, so that no, not all the entire array should be on the same node, for instance, and you can partition the arrays, and this can help you with the big data, for instance. So here I have a short demo. Let me see how I am in time. It's okay. It's a short demo to run a simple for loop. And here is a language agnostic for loop, which goes from 1 to 4. And this is a standard procedure that is followed in research codes, right? Where one starts a for loop and one do some heavy computations inside. So, but this computation here, wait 1 second, mimics just some task that you need to execute, right? And if you depict this as I'm showing you here, you will see that you have a for a task which consists of waiting for 1 second. So in total, if you execute this code on a single CPU, it will take 4 seconds, yeah? But the idea to parallelize that is to execute each task on different CPUs or different cores, in this case 4, right? So that instead of 4 seconds, it will take 1 second on average, right? Yes. So this is the code for Julia, and we will use the threaded mechanism that I mentioned previously. Julia has a function called sleep for waiting some time, yeah? And then we will repeat this over some number of iterations. I will use 4 iterations only in this case. And here is the implementation that I'm doing for the serial version. This is just a for loop, and it will run from 1 to 4, and it will wait 1 second by using the sleep function. So I can write also, instead of the sleep function, a more complex function, but the point here is that it's showing you that some task can be parallelized, in particular this sleep function. So here I'm taking some timing with the bit time decorator that is included in the benchmark tools. Notice that this benchmark tools is not installed by default in the standard library, so you need to add it, as I show you before with the package manager in Julia. And then I define a function with it is a threaded function, yeah. And in this case, I put a decorator. Notice here that the only difference between the serial function and this function, the threaded one, is the decorator. And here I do the same procedure, just waiting 1 second. And finally, uh, I get some timing by using the decorator btime, declaring benchmark tools. So this is the function here. So I can copy this, and I will create a file called sleep threads. It could be there. Yes, it's already there. So I pasted already this code there. And then I load this module, load the Julia module, as you can see here, and I execute the code with this command. So this command is convenient. For instance, if you're in the phase of developing your code and you don't need to you don't want to write an script if it is something fast that you want to execute, right? So otherwise, you can create a batch script and run the script as we have shown you previously. So notice here that this is the A flag that we use for the project. And in HPC2N, you should have this project. A similar flag can be used on the other centers. So here I am requesting one task, and here four tasks per 4 cores per task. Yes, this is the time 5 minutes. Julia is the executable for Julia. Here I request the number of threads, and this is the name of the Julia script. So then I submit this. Okay, I didn't finish the project. 114. Interesting. HPC2N. HPC2N. Okay, yes.
Yeah.
Yeah, HPC2N. And then if you are curious about this, you can check the queue with SQ, and you will see that the job is running. So now you can see that the first task run, which was the serial code, and it took around 4 seconds. And then when you run the code in parallel mode, it took 1/4 of this because we use 4 threads. Yeah. So this is the version for the distributed package for distributed programming. So the idea is similar. Here I declare a function called parallel, and then I use the decorator distributed from the distributed package. And I also need to synchronize the loop, yes, so that all the workers wait here. And this is necessary for the parallel function. So then you can run this as we did previously, and you will get the timing, which is around 1 second. So for this part, we have also some exercises. You can try that. The first one is related to the integration 2D. And here is the tab for Julia. So you don't need to parallelize the code. The task is to run the code for different number of cores. In this case, I provide you the sequence, 1 core, 2 cores, and up to 14. You need to change the fix me strings. Notice that you need to change that in both the batch script here and also in the Julia script here in the number of workers. Yeah? And here is where the underusing or overusing of the system can occur, and this is one case only, yes? Because for instance, imagine that you set here the number of workers to 10, while on the batch script, you request only 5, yes? 5 tasks or 5 cores. Then in this case, you will generating more workers than the available cores, and you will see an over-exceeded resource on the job usage or the top, yes, output. Or on the other side, imagine that here you request 10 cores, right? Or 10 tasks, but in the script, the Joule script, you request only one, yeah? One worker. So in this case, you will be using just 1/10 of the requested allocation. So here you can check this and print out the timings and check what is the optimal value that you need, right? And also this is a challenge that you can follow. Increase the size up to this, submit the file, and use a job usage and top to see if the resources that you requested are the ones that you were targeting. So in the second exercise, I would say more advanced, but it's also more realistic in the sense that you have a data frame that is common in research projects, for instance. And then in this data frame, you have some features or columns, and you want to execute some function or heavy function on the columns. Here I show you how to do some parallelization, yes, over some columns that you want. And in particular, here I show you how to partition the second column, right? To compute the average over several workers. And this can be extrapolated to something more realistic, for instance, in your research project. And at the bottom, you can find the batch scripts that can be used for this exercise. Thank you.